There is a deeply seductive idea embedded in our imagination of the cosmos, the idea that the universe is a vast and open frontier, that intelligence, given enough time and ingenuity, can cross the staggering distances between stars and plant itself like seeds across the galaxy. We look up at the night sky and we see possibility. We see destinations. We see a universe that is fundamentally traversable. And then physics speaks, and it says something far more sobering than we are prepared to hear. The universe is not a frontier, it is a series of prisons. Not prisons built of iron or stone, but prisons constructed from the most fundamental architecture of space, time, and energy. And the walls of these prisons are not merely difficult to breach. They are, to any physical object with mass, mathematically impenetrable. Let us begin not with stars, but with numbers, because numbers are the language in which nature writes its most unforgiving constraints. The nearest star to our own sun, Proxima Centauri, sits at a distance of roughly 4.24 light-years. Now that phrase, light-years, has a way of slipping past us too easily. A light-year is the distance that light, the fastest thing in the known universe, travels in an entire year. Light moves at approximately 300,000 kilometers per second. In a single second, it crosses a distance greater than the circumference of the Earth 7.5 times. In a year, it travels about 9.46 trillion kilometers. And Proxima Centauri is more than 4 of those incomprehensible distances away. Our fastest interplanetary probes, Voyager 1 and Voyager 2, are moving at roughly 17 kilometers per second. At that speed, reaching Proxima Centauri would take approximately 73,000 years, and that is just the nearest star. The Milky Way galaxy stretches roughly 100,000 light-years from edge to edge. The nearest large galaxy, Andromeda, lies 2.5 million light-years away. These are not engineering problems. These are statements about the absolute geometry of the cosmos. But perhaps, you might think, a sufficiently advanced civilization could simply build a faster ship. They could develop propulsion technology that makes our chemical rockets look as primitive as a canoe compared to a nuclear submarine. And here is precisely where physics intervenes with a ferocity that admits no compromise. Because the cosmos does not merely set a practical speed limit rooted in engineering difficulty, it enforces an absolute speed limit rooted in the fabric of reality itself, and that limit is the speed of light. This is not a speed limit in the sense of a posted highway sign that a reckless driver might choose to ignore. It is a limit written into the mathematical structure of space and time, the structure that Albert Einstein illuminated for us in his special theory of relativity. And to understand why that limit is absolute, you need to understand what happens to matter as it approaches it. Begin with a simple question. What does it mean to accelerate an object? In the classical physics of Newton, the answer is clean and intuitive. You apply a force, the object gains speed, and if you keep applying the force, it keeps gaining speed without bound. In principle, you push a spaceship with a powerful enough engine for long enough, and eventually it is moving at any speed you choose. This is the picture we carry instinctively in our minds. But Einstein dismantled that picture entirely. He showed that as an object moves faster, something remarkable and deeply counterintuitive happens to it. Its inertia increases. And by inertia, I mean resistance to further acceleration. The faster an object moves, the harder it becomes to push it faster. Not because of friction or mechanical resistance, but because of an intrinsic property of space and time themselves. Mass, in the relativistic framework, is not a fixed quantity. It is an expression of energy, and as kinetic energy accumulates in an object, that object becomes effectively heavier in the sense that it resists further acceleration with ever-increasing stubbornness. This is the content buried in the most famous equation in all of science. Energy equals mass times the speed of light squared. What that equation is really telling you is that mass and energy are not separate commodities. They are different faces of the same thing. And that equivalence has a devastating consequence for any spaceship trying to approach the speed of light. As the ship accelerates, its kinetic energy grows. And because energy and mass are equivalent, the ship effectively becomes more massive. A more massive ship requires more force to accelerate. More force requires more fuel. More fuel means the ship is carrying more mass. More mass means it needs even more fuel. You are caught in a recursive trap, a cascading demand that grows without bound as you approach the speed of light. Let us be concrete about the scale of this demand. Imagine you want to accelerate a modest spacecraft, just 1 metric ton of payload, to 90% of the speed of light. The kinetic energy required is already equivalent to roughly 2 billion times the energy released by the atomic bomb dropped on Hiroshima. Push that to 99% of the speed of light, and the energy requirement increases by more than a factor of 7. At 99.9%, it has climbed by a factor of 22 compared to 90%. The energy curve does not rise gracefully. It becomes nearly vertical as you approach light speed. To actually reach the speed of light, you would need infinite energy. The universe is not hiding that energy somewhere waiting to be harnessed. Infinity is not an engineering target. It is a mathematical statement that the goal is impossible. Now, here is where the problem deepens from merely daunting to genuinely catastrophic. We have been talking about the energy required just for the spacecraft, just for the payload, but energy must be carried somehow. And the most efficient way we know to carry and release energy is through matter, through fuel. The Tsiolkovsky rocket equation, derived in the 19th century and still mercilessly relevant today, tells us that the ratio of fuel mass to payload mass grows exponentially with the velocity change required. For chemical rockets, reaching Earth orbit requires carrying roughly 9 kilograms of fuel for every kilogram of payload. For a relativistic journey, the numbers become almost surreal. To accelerate a single kilogram of payload to even 10% of the speed of light using a perfect rocket with perfect efficiency, meaning one that converts every gram of fuel into pure, usable thrust at the absolute theoretical maximum, you would need to carry approximately 22 kilograms of fuel. That already sounds manageable. But 10% of the speed of light is still 30,000 kilometers per second, and the nearest star would still take you over 40 years to reach. Push to 50% of light speed and the fuel-to-payload ratio climbs into the thousands. At 90%, it is in the hundreds of thousands. Even if we imagine an antimatter propulsion system where matter and antimatter annihilate each other to release energy with 100% efficiency, the numbers remain ruinous. To send a 1,000-kilogram spacecraft to 90% of the speed of light and then decelerate it at the destination, because you also have to stop, you would need millions of times the ship's mass in antimatter fuel. The total antimatter energy budget approaches the annual output of our sun, and antimatter does not exist in bulk anywhere in the observable universe. It must be manufactured, particle by particle, in accelerators. The entire history of human particle physics research has produced less than a gram of anti-hydrogen under extraordinarily controlled conditions. To bridge even the nearest stellar gap with a crewed mission traveling at a significant fraction of light speed, using any physics we understand, would require energy resources that dwarf the total economic output of a planetary civilization over centuries. But let us be generous. Let us grant a hypothetical alien civilization, a technology far beyond anything we can currently conceive. Let us say they have mastered exotic energy sources we have not yet imagined. Let us say they can extract energy from vacuum fluctuations or harness the output of their star with perfect efficiency. Even then, the physical laws governing mass, energy, and relativistic momentum do not relax. The mathematical structure of space-time does not offer any shortcuts. The universe does not contain any bypass mechanism for the relationship between velocity and inertial mass. These are not contingent properties of our current technology. They are absolute properties of the space-time geometry in which every possible civilization must exist. Consider what the universe looks like from this vantage point. The Milky Way contains somewhere between 200 billion and 400 billion stars. They are distributed across a disk roughly 100,000 light-years wide and perhaps 1,000 light-years thick in the vicinity of our own sun. On average, stars in our galactic neighborhood are separated by roughly 4 to 8 light-years. Now imagine that every one of those stars harbors, somewhere in its family of planets, a civilization as old and as capable as we might dream of any sufficiently advanced intelligence being. Each of those civilizations faces exactly the same physics we do. Each of them is separated from its neighbors by light years of lethal, empty vacuum. Each of them confronts the same exponentially escalating energy demands, the same tyranny of the rocket equation, the same fundamental impossibility of moving mass at relativistic speeds without consuming fuel quantities that beggar the imagination. The interstellar void is not simply cold or empty in the way that an unfurnished room is. Empty. It is cold in a way that makes the concept of cold almost abstract. The temperature of intergalactic space approaches 2.7 Kelvin, just barely above absolute zero, the point where molecular motion itself ceases. It is saturated with cosmic radiation, high-energy particles accelerated by supernovae and active galactic nuclei that would penetrate even substantial shielding and deposit their energy as ionizing radiation in any biological tissue. A spacecraft traveling at even 1% of light speed impacts the thin interstellar medium, those sparse hydrogen atoms distributed at roughly 1 atom per cubic centimeter, with the energy equivalent of a continuous high-velocity particle beam. The faster you travel, the more destructive this becomes. Shielding is possible, but shielding has mass, and mass demands more fuel, and you are back inside the same merciless loop. There is a conceptual shift that I want to invite here, because I think it changes the nature of the Fermi question fundamentally. We tend to frame the question of alien contact as a problem of motivation or communication. Perhaps they do not want to contact us. Perhaps they are sending signals we do not know how to receive. Perhaps they are too alien in their cognitive architecture to recognize us as worth contacting. All of these framings accept, implicitly, that physical travel between stars is at least theoretically achievable, that the question is one of will or method rather than physics. But physics renders that framing moot. The more accurate framing is this. Given the energy requirements of relativistic travel and the thermodynamic constraints on any material system, interstellar civilizations are not merely rare or unsociable or silent. They are physically isolated from one another by the same laws of nature that shape the atoms from which their bodies are composed. The constraint is not a fence. It is gravity itself. It is inertia. It is the speed of light. It is the exponential relationship between kinetic energy and relativistic mass. These forces do not yield to intelligence or ambition or technology. They are the bedrock of physical reality. Now, there is a class of objection that arises at this point, and I want to address it directly because it is an honest objection. What about generation ships? Vessels so large and so complete that they function as self-contained ecosystems across the millennia, carrying a population that reproduces and thrives across thousands of years of travel at low, chemically achievable speeds. This is not a physically preposterous proposal in the same way that a light-speed drive is physically preposterous. Slow ships might be possible in principle, but the implications of this scenario actually reinforce the isolation argument rather than defeating it. A generation ship traveling at, say, 0.1% of the speed of light would take over 4,000 years to reach Proxima Centauri. The civilization that launched it would be utterly unrecognizable to the civilization that eventually arrived. The resource requirements for constructing and maintaining a self-sustaining biosphere capable of housing hundreds or thousands of individuals for thousands of years, with the structural integrity and redundancy needed to survive micrometeorite impacts, radiation damage, mechanical failure, and the inevitable biological and social crises of closed ecosystems, are genuinely planetary in scale. You are not talking about a spacecraft. You are talking about moving a small world through the void. And you are doing it on a timescale so vast that the entire history of recorded human civilization would fit comfortably inside the journey time. Even granting all of this, the number of such ships any civilization could plausibly launch is vanishingly small, and the probability of any such ship being aimed at our obscure corner of the galaxy approaches zero. The size of the galaxy ensures that even exponential self-replication, building ships that build more ships, would take millions of years to colonize even a fraction of the Milky Way at sublight speeds. And millions of years is a long time in cosmic terms, but it is not infinite. The galaxy is 13.5 billion years old. If there were civilizations old enough to have pursued that strategy with sufficient determination, the signs of their presence at galactic scale should arguably be detectable. The silence around us is itself a form of data. There is one more physical constraint that I find particularly illuminating, not because it adds a new barrier, but because it reveals the depth at which these barriers are embedded in nature. The second law of thermodynamics tells us that any physical system, any engine, any life support mechanism, any computation produces waste heat. There is no process in nature that converts energy into work with perfect efficiency. Every act of propulsion, every act of maintaining a living organism against the entropy of a cold universe, every computation run by an artificial intelligence navigating a starship generates entropy. Managing that entropy in the cold void of space requires radiating waste heat into the environment. The thermodynamic budget of a relativistic spacecraft is not merely large, it is civilizationally demanding, a continuous drain on the energy resources of whatever society is underwriting the journey. And the longer the journey, the more total entropy must be managed, the more total energy must be expended just to maintain order against the universe's persistent tendency toward disorder. This is not pessimism. This is not a surrender to limitation. This is what it looks like to take the laws of nature seriously rather than treating them as provisional obstacles awaiting sufficiently creative engineering. The universe was not designed for biological creatures to traverse it. It was not designed at all in the intentional sense. It simply is, with the structure it has, governed by the mathematics it obeys. And that mathematics is deeply inhospitable to the movement of matter across the yawning emptiness between stars. The most profound implication of all this is perhaps philosophical rather than technical. If we accept that the physics of special relativity, inertia, thermodynamics, and the rocket equation apply universally, not just to us, but to every civilization that has ever existed or will ever exist in this cosmos, then we arrive at a picture of the universe as an archipelago of isolated islands of warmth and complexity, each one separated from the others by oceans of cold and emptiness so vast that no ship can meaningfully bridge them on timescales relevant to any continuous civilization. Life, wherever it has managed to ignite the improbable flame of awareness and intelligence, is almost certainly doing so in profound isolation, bounded not by the limits of its own ambition, but by the absolute geometry of the cosmos it inhabits. That picture is not diminishing. It is, in its own way, extraordinary. It means that whatever intelligence arises in a given solar system has to find its meaning and its purpose within the confines of a single star's gravitational family. It means that the universe, for all its staggering scale, parcels its conscious moments into sealed vessels, each brilliant and self-contained, each confronting the questions of existence without the possibility of consultation with distant others. The physics that